said, my name is Jody Meadows. I've been with Greenheck for about 25 years, and the product that I'm responsible for is centrifugal fans. So that includes utility sets and fan arrays. So for the next hour or so, we're going to go through some fan array data. I want to cover what a traditional fan system versus a fan array looked like a couple of decades ago. And then we'll do an overview on housed and unhoused plenum arrays and give you some different things to look at there as you're making selections for those. Also some different things to consider as you're making fan array selections. And I've got a couple of slides on motor technology and some different things that are going on in the industry. Certainly time for questions, as Chris said. If you have any questions as we go, send them through the chat function. And then if we have time at the end, I have just a couple of slides on FEI, which is becoming a bigger topic for everybody across the nation. All right, so let's dive right in. So if we think back 40, 50 years ago, what was very common to find inside of an air handler was an axial style fan, like I'm showing on the screen here. Vane axial style fan, a lot of times the propellers were variable pitch propellers so that they could be adjusted in order to accommodate whatever the flow is required through an air handler. And then the transition kind of went to a housed centrifugal fan. So what I'm showing you here is a double width fan. You'll notice that there's a large motor. It's belt drive. In many cases, they utilized IVDs or inlet vane dampers, again, to meter flow through the fans because a lot of these fans were not on VFDs at this point in time. Then the industry moved more toward large unhoused plenums, still belt drives, still single motors, still single fans in a lot of cases. And then more recently, we've seen the trend move toward more smaller fans. And a big reason for this is because VFDs became more readily available. Permanent magnet motors or electrically commutated motors became more available and more cost effective. And the most recent trend now is toward fan arrays. So fan arrays are more compact, lighter weight, and there's a lot of benefits that come along with fan arrays, which is what my next slide is. So why do we use a fan array instead of our traditional fans, either housed or unhoused centrifugal fans? Well, wheel size aligns better with motor speed. So what I mean by that is when you look at nominal motor speeds, they're going to align better with smaller fan sizes. So if you look at a large belt drive housed double width fan as an example, they're going to spin at maybe 600-700 RPM. Well, most motors in the industry, or the common motors in the industry, are going to be a 4-pole 1800 RPM motors. So you have to use belts and drives to get that down to a fan speed. So with direct drive, smaller fans, you get better alignment with nominal motor speed. Redundancy is also a big advantage. So if a fan does go down in a system, the system can typically ramp up to cover some of the performance of that down fan. Whereas with a housed centrifugal fan or a unhoused centrifugal fan with a one motor, any failures in the motor, the drives, the bearings could mean that the system is down entirely. Low maintenance, so in a lot of cases, the motors are going to be direct drive and most of the time permanently lubricated so that there's virtually no maintenance on the motors. Serviceability is an obvious one. You become much more capable of dealing with the lighter weights as a single person, where if you think about changing out a 100-horse motor on a large double width fan, that's going to take a small army to do it versus pulling a 5 or 7.5 horsepower motor off of a fan and replacing it. Lower sound, when you got a large fan, whether it's a housed or unhoused, they're creating a lower frequency, which is going to transmit through buildings and structures more. Where if you got smaller fans spinning at higher speeds, they're creating higher frequency sounds, which are much easier to attenuate. Lower vibration is kind of intuitive as compared to the traditional fans where there's more moving parts, belts, drives, pulleys, bushings. With the direct drive fans, you have less vibration. shorter axial length. In a lot of cases, we've got compact plenum style fans that are now hung on the wall, so they're maybe 18 inches deep versus maybe 4 or 5 or 6 feet with the traditional fans. And then operational flexibility. There's a lot more flexibility with variable volume systems and more controllability. So what I'm showing you here is a modular housed array. It's our model HPA, and it's designed to ship to a job site in pieces, so individual fans per skid. And then it can be hauled into a space with a two-wheeler. A guy or two can stack them up and erect them in place, bolt them together, and you have your array. One of the nice features of this fan is that it has internal attenuation. So there's 2 inches of sound attenuating duct all the way around the inside of that fan. And what it does is it allows the outlet sound to be about 8 to 10 dB below a typical fan that does not have attenuation. So it's a very good fan for sound sensitive applications. And the one thing to note here is that there is an efficiency impact because that fan is located inside of the box. So we'll talk a little bit more about that. Another nice feature is that they are internally isolated. So you don't have to have isolation underneath this fan array. It can sit on the floor, and the fans themselves are isolated from the rest of the structure. So that's a nice feature as well. That also makes it very easy to remove a fan. So there's about 4 fasteners that hold that whole power pack inside of the box. And those can be removed and relatively easily removed from the fan and replaced. All right, so now let's look at the difference between a housed plenum array and an unhoused plenum array. So we have a couple of different examples here. Specifically, when we talk about the performance of an open array, we know that there's velocity vectors that communicate between the wheels, and that velocity vector, those velocity vectors are going to change depending on how fast the wheels are spinning and how close they are together. So when we look at most fans that are found in an array configuration, they're typically going to be AMCA sound and air certified. And what that means is each one of those individual fans were put on a chamber and tested, similar to what I'm showing you on the screen here. And then what we assume is that if there's a 4-fan array, you just take the performance from each individual fan, multiply it by 4, and that gives you your performance for the fan array. Well, what we wanted to understand was if that is truly the case. AMCA does not have a fan array certification at this point in time. So there's a lot of assumptions made around the communication of those wheels that we just talked about. And so Greenheck really wanted to set out to understand that a little bit better. AMCA says essentially if you put 1 wheel diameter in between fans, there's assumed to be no performance losses, so no system effect takes place. And you would expect you'd expect your performance to be a multiple of each individual fan selection. So we set out to really understand this in much more depth. We wanted to understand how the velocity vectors, communicate with one another based on velocity. So how fast we're spinning the fans. And then we also really wanted to understand the impact on spacing. All right, so how do we quantify this? Well, we put a test plan together. And what it amounts to is setting up a fan array and basically adjusting the fans closer and further apart in 1-inch increments horizontally and 2-inch increments vertically. And then we're going to run that whole setup in each one of those different configurations at 4 different speeds. Okay, so it amounts to about 480 different tests. And so we set out to do that, and I'm going to try to play a video for you quick to kind of illustrate the testing that we did. And so here it is. Let me see if I can get it to play for you. All right, so if you notice down here in the bottom right corner, there's a whiteboard. And so there's the date that we started this testing, back in October, early October of 2018. And if you watch this video just cycle, what you'll notice is that the wheels move closer together vertically and horizontally in 1-inch and 2-inch increments. And so we go through each setup over the course of time. And I'm going to speed it up a little bit just so you don't have to sit through 6 minutes of the same video, but you'll see the fans move closer together and further apart. So every one of these setups, we're going to run the fans at 4 different RPMs, collect the data, and analyze it. So you can see we're about a month into the testing right now, and we're going to jump ahead just a little bit. So now we're in November. And by the end, so this is right around Christmas time, 2018. So by the end, what we were able to do was create some formulas to actually predict the performance of these wheels based on proximity and velocity, or what RPM you're going to spin them at. So in the end, we spent about 3 months testing the fans. We ran almost 500 tests. And now what we can do is we can optimize fan performance based on the data that we collected. So we took that data and we baked it into our CAP system. So if you're familiar with our computer-aided product selection software, when you go in to make a fan array selection specifically for an MOA, we ask you for the envelope. So we ask you for the width and the height of your fan array. And so you enter your fan array width and height and your performance, and CAP spits out an optimized selection. And then you have the ability to pick the fans or the fan array that best fits your needs, whether that's based on efficiency or cost or sound or number of fans. You're able to pick the best fit for your application. So I've got an example as we talked about the communication and wheels. So these are selections that I made in our CAPS program, and these are 22-inch wheels. I picked a design point of 7,000 CFM at 3 inches of static. So to hit that performance with a 22-inch wheel, our fan RPM is 1635, and brake horsepower is 4.68. So now let's take that same wheel and put it in a fan array. All right, so my example here has 96 inches between centers. So we've got 8 feet of spacing between the wheels, so they're very far apart. And in this scenario, you can see the volume, we just multiplied by 4. Static pressure remains the same. Fan RPM is not impacted. There is no system effect at this point because the wheels are far enough apart. And our brake horsepower is a factor of 4 as well. So now let's start to put those wheels a little bit closer together. So we've got 22-inch wheels at basically 1 wheel diameter apart. Again, volume remains a multiple of 4. Static pressure remains at 3 inches, but now we have to spin the wheel a little bit faster, 1.3% faster, in order to hit that same performance. And you'll also notice that brake horsepower went up, and it goes up by a cube, so it's 4.3% more brake horsepower to hit that same performance point. Okay, let's take that one step further. So now we have a half a wheel diameter. Again, static pressure and volume stay the same, but now our fan RPM goes up 3.3%, and brake horsepower goes up 11.1%. So there's a real life impact in putting these wheels closer together. And I don't know about all of you on the call, but I've been out in the industry looking at fan arrays, and a lot of times you see wheels or fans stacked very close to one another. So this is a half wheel diameter in between. I've seen them stacked a lot closer than that. So it's important to take into account certainly proximity and what the communication is that's taking place between the wheels. Now, in some applications where it's just a single air handler, it's probably not a huge impact. So if you don't hit your performance, you spin the wheels a little bit faster and get to the performance point that you need. But when you think about this on more of a mega scale type application where you're moving over 1 million CFM and you might have 150 motors in the application, every fraction of brake horsepower adds up, and it adds up fast. So it can be important on a larger scale. Anytime we're interested in efficiency, it's something to really be aware of. So when we look at housed versus unhoused, again, our housed array is very good for sound sensitive applications. And our open array, it really lends itself to retrofit applications. And when we take a look at the performance differences, I've got some examples here again. So I made a 4-fan selection at 32,000 CFM and 3 inches of static in both a housed and an unhoused array. So you can see our brake horsepower in the housed array is 21.8, and in the open array, it's about a 10% reduction, so 19.69%. So that was the impact I was talking about by putting a wheel inside of a box. There is a little bit of a penalty for doing that. Now, outlet dBA, in the case of the housed array, it's 72 dB. With the open array, it's at 84 dB. So the penalty there is that there is a little bit more sound associated with the open configuration. But because there's less materials and no attenuation, the open array configuration is going to come in a little bit lower cost. So again, it depends on your application, but from an efficiency perspective, the open configuration is definitely going to be a little bit more efficient. All right, so when we think about retrofits, we think about that maybe 4 to 5 decades ago, where we've got big double width centrifugal housed blowers or large plenum fans, 100 horsepower motors, belts and drives. The retrofits in those applications can be difficult. In a lot of cases, the larger fans need to be cut into pieces and removed physically, piece by piece from the air handler. And so what we do with the modular array is we provide it basically in components. It's kind of like an erector set. So all lightweight, small enough components that can be managed by a single person. And they're designed to be erected or put up in the air handler on site. All right, so we also have a kind of a turnkey package that goes along with our modular array. We have a high power, high voltage, and a low voltage power panel, and we provide all the wiring that goes from the panels to the fan arrays. So really a turnkey package designed to take a signal from a BMS and operate based on either a static pressure reading or a constant CFM. Now, one other thing to consider, and pretty common in the industry, is the requirement for a backdraft damper on a fan array. So again, as we think about efficiency, a backdraft damper is an important piece in some applications. If a fan does go down, the backdraft damper is designed to close and prevent air from backflowing. Well, the reality is, if a fan doesn't go down, you're paying a price to keep that damper in place. You not only have to buy the damper, but you also have to pay in terms of efficiency to keep that damper open. So I made another selection here. We've got 2 fans. We've got a housed fan without a backdraft damper, and we've got a housed fan with a backdraft damper. And the 2 selections are the same. The only difference is the damper, and you can see how the RPM on the dampered fan is a little bit higher, and therefore brake horsepower is a little bit higher. In this case, 3.1%. And I just took some rough estimate and put 3% per year. So each fan in the array would potentially cost 3% more to run with a backdraft damper versus an optional blank off panel. So the solution that we recommend in lieu of a backdraft damper is going to be a blank off panel. Blank off panel is kind of like a cake pan flat disc, and they're designed to be bolted in the inlet of a fan. So if you have a fan that goes down, your controls will indicate or send an alarm to the BMS. If you have maintenance on site, they can go in and in a couple of minutes put a blank off panel over that fan that's down until repairs can be done or the fan can be replaced. So what we estimate is about 6 to 7% backflow through that fan. So that's a relatively low volume of air in most cases, depending on, obviously the size of the fan array. Um, but for a short period of time, I think that's acceptable for waiting for maintenance to come in and put that blank off panel in place. So a blink off panel is a good option. It's something we recommend instead of paying for the efficiency of a damper, just in case it's needed. All right, so also from a control perspective, there's a number of different ways that we see fan arrays controlled in the industry. Traditionally, each fan would get a VFD, as I'm showing over on the left-hand side. So you send your power and you send a signal to the VFD, and the VFD communicates with the motors. We've also seen single VFDs powering multiple fans in the array. In this scenario, you do have to also include contactors and fusing between the VFD and the motor. So there's some additional wiring and setup that takes place in the field. But conversely, the fans over on the right or the motors over on the right are permanent magnet or EC style motors, where they either have an integrated drive, and most typically they'll have an integrated drive. In that scenario, you can send signal and a power directly to the fan. If you have a BMS, it can communicate directly to each fan and receive via BACnet, receive communication back and feedback in case there's a motor that goes down. You would get an alarm in that scenario. So different ways to communicate with the VFD and or permanent magnet motors within fan arrays. Okay, so the next topic is sizing motors for direct drive fans. All right, so when we think about sizing motors for a belt drive fan, there's a couple things we think about. So brake horsepower of the fan. So we know what the brake horsepower of the fan is for a specific design point. And then what we're thinking about then is what's the nominal horsepower of the motor that I'm going to apply. So if you have a 4.5 brake horsepower fan, a 5 horsepower motor is probably enough. Well, the same is true with a direct drive fan. So I'm again thinking about the brake horsepower of the fan at that design point and what horsepower motor I'm gonna utilize. But the other thing that you have to also consider is fan RPM versus motor RPM. All right, so and this is what I talked about a little bit earlier with sizing motors and wheels, sizing wheels to fit with nominal motor horsepower, nominal motor RPMs. All right, so again, as an example here, I've got a selection that's 20,000 CFM at 4 inches of static. It's a 4-fan array, and the design point puts the fans at a 2,507 fan RPM, and the brake horsepower is 3.6 in each one of those fans. So within our CAPS program, you'll have 2 different selections that you can make. One will be with a 4-pole or 1,800 RPM motor, and in that scenario, we'd have to overspeed the motor, so run the motor at 85 hertz. Okay, and we can do that with a 5 horsepower motor. The other scenario that you can select is going to be a 2-pole motor, 3,600 RPM motor that you would underspeed. So we would run that under 60 hertz. We'd run it at 41, and that would require a 7.5 horsepower motor. Okay, so the reason for that is horsepower is equal to torque times RPM divided by a constant. All right. So I've got an example here. It's a 10 horsepower motor, 4-pole. And what I'm showing you on the graph is that motor running at 60 hertz. So we take that 10 horsepower motor and we run it at 60 hertz. You can see the blue circle is right at the constant torque, constant horsepower intersection. And so we're going to get a full 10 horse at 60 hertz. Now, based on that formula, if we take that same motor and we slow it down to 30 hertz, so we reduce our RPM by roughly half, what you're going to have is horsepower is derated. It's a linear deration in horsepower. So at 30 hertz, we only have 5 horsepower available. Okay, so that's the reason when we underspeed a fan, you have to bump up the horsepower on the motor. Now, conversely, if we take that same 10 horsepower motor and we overspeed it, so we run it up to 90 hertz, now we're on the constant horsepower line, and what you find is that RPM goes up at the same rate that torque comes down, so you end up with that same 10 horse in an overspeed condition. So the moral of the story is you're always better off to overspeed a motor rather than to underspeed the motor. And so again, when you're making selections, the important thing to remember is to make your selections as close to nominal motor RPM as possible. And that will have the least amount of impact on the motor sizing. All right, so one other thing to consider when you're making your fan array selection is, again, motor RPM and size. So of course, you make your selection, and that's one of the factors that can affect the price of the fan. So that's another important feature to take into account as you're making selections. And Chris, I don't know if we want to stop and field questions on the fan arrays.
No one's asked any questions to this point. Just a reminder to everybody to put your questions in the chat. We are happy. Jody's obviously done this presentation more than a few times, and we want to make it beneficial to all of you watching. So please ask questions if you have them. I think you can just keep going, Jody.
All right.
Yeah, hey, I have a question. This is Scott.
Hey, Scott.
So when you're selecting motors above 60 hertz, what are penalties for doing that? You're saying it's more efficient, but I get nervous selecting something at 80 hertz versus 40 hertz. So does it have different noise characteristics? Is there any downsides to doing that?
Yeah, that's a really good question. I would say this is probably one of the commonly misunderstood things in the industry. You know, when we talk about putting a VFD on a motor, most people think about that in terms of being able to slow a motor down, not necessarily speed a motor up over 60 hertz. So, you know, we work directly with ABB, and VFD rated motors are designed to go up to 90 hertz with their standard design. So I would say that there is no impact. Not only bearing life is not impacted, or winding, life isn't impacted. So VFD rated motors have Class F insulation, which protects them from heat, and the bearings are sized in most cases to run at 2-pole speeds. And that's one of the features I know ABB works into their motors. So if you took as an example, a 2-pole motor and a 5-horse and compared it to a 4-pole motor and a 5-horse, the bearing size is identical. So in theory, a 4-pole motor can run at 2-pole speeds and not have any impact on either winding life or bearing life. Does that make sense?
Yeah, so it's basically I shouldn't worry about it in the case of I still have to have a safety factor. You know, I'm not going to pick it at 89 hertz. And I'm looking at the sound, I'm looking at the size, I'm looking at the first cost. So I should weigh all those selections the same and kind of get out of my mind that above 60 hertz I get nervous and I shouldn't be.
Yeah, I would say that's 100% true. We recommend, we don't like underspeeding conditions because it does impact the cost and the size of the motor in typical scenarios. So we always recommend overspeeding. It is perfectly safe. The motors are designed and to accommodate the overspeed conditions. So yeah, it's a kind of a mind shift in some cases, but that's the reality of it. We work directly with a lot of OEMs that build air handlers, and that's something that they have been doing for many, many years, and they're very accustomed to it. But the rest of the HVAC industry has been a little bit slower to adopt the overspeed conditions. Definitely.
Okay, thank you.
Great question.
We did just get a question from Mark. Does overspeeding impact the VFDs?
So I would say again, a VFD. I'm not certainly a VFD expert, but you know, all the VFDs that we use and provide in our applications are HVAC designed VFDs. So you know, the motor is designed to be oversped, and I would assume that therefore the drive is as well. I know there's carrier frequencies and things that can be manipulated, but that is not something we typically have to adjust on the VFD. Parameters are set appropriately, and we overspeed motors on a regular basis. So I don't think there's any harm on the VFD front.
And where, you know, Jody had spent some of his time previously being an application engineer focusing on applying the products to the field. Greenheck does have an entire team behind him of design engineers working and designing and making sure all the components fit within the standard. So Greenheck does have an engineering team verifying that the particular VFDs they use are intended for the applications Greenheck plans on using them. So there should be no worries about testing and the VFDs that they've selected when you're getting a Greenheck provided factory VFD.
Yep, very, very true. We test everything thoroughly. Okay, so I've got a couple slides here on motor technology. So one of the terms that we use broadly across the Greenheck family is very green. And when we talk about very green, in a lot of cases, we think about the green broad ocean style motor up in the upper left-hand corner of the screen. And those are typical, very typical in most of our applications, but they are they're usually less than 1 horse and single phase. So in the fan array world, most of the motors that are utilized are at least 3-phase and above 1 horse. And so there's a number of different motors and motor technologies that can be used in fan array applications. I have some of them on the screen. One that we like to utilize, and specifically in our housed plenum array, is a ferrite-assisted synchronous reluctance motor that comes from ABB. So it's a relatively new motor that has an integrated drive, and it is a 3-phase EC motor. We offer it up to a size 10 horse. And let's talk about the differences here when we compare this to an AC induction motor. So I've got a rotor here in front of you on the left-hand side of the screen. This is a typical AC induction motor rotor, and it's steel laminated discs stacked up on the shaft. And the way it works is there's an electromagnetic field that's induced into the stator in the motor and also into this rotor. And they oppose one another and they rotate. So when we talk about a synchronous reluctance motor, it's similar in construction. The difference is there are grooves or channels that are cut into that rotor, and those grooves or channels align very well with the windings in the stator. So there's an improvement in efficiency from those directional grooves. And when someone says ferrite assisted, so basically it's just a ferrite magnet or a refrigerator style magnet that's packed into those grooves or channels, and that increases the magnetic flux, and there again increases efficiency. So the AC induction rotor is what we consider an IE3 efficiency rotor. Synchronous reluctance is an IE4, and then the ferrite assisted gets it all the way up to an IE5 level of efficiency. And so to give you a better understanding of that, what I've plotted here is IE3 efficiency, and that's a NEMA premium, so it's the minimum efficiency required for a 3-phase motor to be sold in the US. And what you can see here, if we look at the curve or look at the chart, is that the 5-horse motor is about 89% efficient. And when I show you now IE4, this is another 10% reduction in losses, and that same 5 horsepower motor is about 91% efficient. And again, as we look at IE5, so IE5 levels of efficiency is another 10% reduction in losses, and that same 5 horsepower motor is now about 93% efficient. And the synchronous reluctance EC titanium motor is IE5 level efficient, and I plotted it here on the chart so that you can see it. So it's a very efficient package that lends itself very well to a lot of applications because it is a NEMA footprint motor. So it can be a direct replacement for a NEMA style motor. And the big advantage is that it's not only very efficient at full load, but as I'm showing you here on the chart, it's very efficient even at turn down. So the blue line is our system curve, and the yellow line represents that AC induction motor that's in the lower left-hand corner. And you can see that they start out just below 80% efficient and at full load, but then as you turn them down or slow them down, the efficiency starts to taper off some. So the dotted gray line is like a synchronous reluctance or permanent magnet motor. Again, very efficient at full load, but as you start to slow it down, it starts to taper off as well. And then the solid gray line is represented by the EC titanium motor. And the EC titanium, you can see, has pretty good separation, even at full load, but also at turn down. So there's probably 10 points of separation between the turn down of an AC induction motor and that EC titanium. So very efficient motor, not only at full load, but also turn down. And any of the fan arrays that I've worked with, they never seem to run at full load. They always seem to run somewhere below that. So great motor to help maintain efficiency in those variable volume systems. Any motor questions, or should I go right on through to a couple of slides on FEI?
I see no questions in the chat.
Okay. So, sounds good. So I've got just a couple of slides on fan efficiency. Then I can go through. So fan efficiency index. As we think about fan efficiency, historically we've always thought about that in terms of static efficiency or total efficiency. All right. So it's basically a measure of power output divided by power input. And today, and so that's really just looking at aerodynamic losses and bearing losses. So it's not looking at the full picture of fan efficiency. All right, so static efficiency is really just looking at aerodynamics and bearing losses. As we move forward, FEI, or Fan Efficiency Index, is a measure that takes a look at everything from line power in to air coming out of the fan and everything in between. So any and all losses are taken into account with FEI. So what is FEI? FEI is a reference fan electrical input power for a design point divided by the actual. And if you want to get into the details of what the math is or the formulas are to get to that, there's 220 pages of AMCA documents that you can purchase and read up on. They're out there. Otherwise, the simple thing to do is just look for the sticker that shows that AMCA Sound Air and FEI are verified and provided by the manufacturer. So anything that has an FEI rating on it coming from Greenheck is going to have this AMCA FEI sticker on it. So I've got a couple of examples here. So I chose a design point of 10,000 CFM at 3 inches of static. All right, and when we look in the AMCA documentation, it tells us that the baseline input electrical power should be 7.96 brake horsepower. All right, so 7.96 brake horsepower. And that doesn't matter what fan is utilized for that application. It can be any fan, and it would apply to all fans. Okay, so let's take a look at a utility set. for that specific design point. So 10,000 at 3 inches, our baseline power is 7.6. And what I've got here is I've charted the sizes 18 through basically a 36, and show you a column with a baseline brake horsepower that we're trying to hit of 7.96. And the actual fan power, smaller fans spinning faster are going to be higher brake horsepower. And over on the right-hand side is your FEI calculated. And you see that on a size 22, there's an inflection point. So size 22 and larger, we start to get to the point where we're a 1.0. The larger the fan, the higher the FEI, the lower the brake horsepower, so the better the ratio. So essentially, what FEI is doing is it's encouraging selections to be made higher on the curve. Right, so larger fans higher on the curve in more of the high efficiency, low sound region of the curve. We traditionally pick fans a lot in the low efficiency and high sound region because a lot of times they're lower cost fans. So FEI helps really drive the behavior to selecting fans that are higher efficiency. So what I put up here now is the FEI efficiency bubble. So anywhere within that yellow, or excuse me, that red circle would be 1.0 FEI or better. All right. So again, FEI is driving the decision to make better, more efficient fan selections. And every fan and fan design has its own efficiency bubble. So this is a square fan with a centrifugal wheel inside of it, not a super efficient fan. It still does have an FEI bubble there where you can see 1.0 or better lands inside of that red circle. But you can take a more efficient fan like a QEI where you've got straightening vanes and more structure inside, helping it be more efficient. You can see that the efficiency bubble is much, much larger for a higher efficiency fan, which is intuitive. So selections anywhere within that red circle are going to be FEI of 1.0 or better. Ultimately, AMCA has an FEI certification, again, taking into account all the losses from your power in, anything through VFDs, takes into account the type of motor that's being used, if it's a belt drive, what losses are associated with the drive combination and or bearings, and then of course your aerodynamic losses that are part of your fan design. So again, the industry trend is to move toward more direct drive fans for all applications, and a big part of that is FEI. So you don't have to take losses for bearings and drive combinations. So it's really helping drive the industry toward more efficient motors, more efficient motor and drive combinations, as well as direct drive fans. In any of our selections within caps, if you're looking for FEI, you can find it in the sizing grid. And this is one of the things that has become more and more prevalent as FEI grows in popularity across the country. I know your region of the country is offering some rebates for high FEI selections. So you guys are a little bit ahead of the curve, and that's good to keep everybody aware of efficiency and making good selections for fans. And with that, I'd open it back up for questions.
Well, as we wait for questions, thank you, Jody. It's a ton of information. I always like to remind everyone, we don't expect you to remember everything we've talked about today, just that Greenheck knows the product, they have the offering, and to remember to give Dorse and Greenheck a call the next time you have an application where you might need a plenum fan or a fan array. Even this year, I've seen some engineers take some of our standalone plenum fans and basically build their own fan array, not realizing we had an offering like the OPA that could be a from the factory, ready to go with the sheet metal, with the supports. So it's about getting some exposure and just knowing that Greenheck has a full product offering of fan arrays for new built up systems, or in most cases, replacement for those large built up air handlers.
Yeah, hey Jody, considering that there's not really an AMCA standard, if people were looking at different manufacturers and trying to decide which one to pick over the other, saying that they're using the same wheel style in an open array or a housed, what do you think they should be looking at to get the best thing for themselves?
I think the general thing to take away from all the testing that we did is more spacing between the wheels is going to give you truer performance. If you are inside of one wheel diameter spacing, there is going to be a system effect that needs to be accounted for. So I think the biggest caution there is if you know your fans are going to be stacked tight together, I would just make sure that there's enough range in motor horsepower and wheel performance capabilities to, just know that you're going to have to speed it up. And generally across the industry, I would say that most are using just a single fan performance and multiplying it by the number of fans, and not taking into account system effects. So those are just the things to be aware of. And as I kind of mentioned, in most small air handlers, it's not the end of the world if you just have to spin the fans a little bit faster to overcome that system effect, but it's something to be aware of.
Excellent. All right, I don't see any other questions asked. So I guess we'll end it here. Jody, thanks again to all of our guests. Thank you for joining us. Again, this is the last one, so you don't have to listen to my voice next week. You guys get a reprieve. Please provide us your feedback of everything that was good or bad about the power hours over the last 2 months. We have thick skin, so please let us know. We want to make these better and as great as possible for everyone. So thanks again to Jody and our Dorsey team, Scott, Blake, and John. We look forward to seeing you the next time we do this. Thank you, everyone.
Thank you.